Welcome to Differential Equations, section 3.6. All right, in this first problem, we have a second order differential equation, non-homogeneous. We have a driving function on the right-hand side and two initial conditions. So, we start off solving the homogeneous problem, set up the characteristic polynomial. I get two complex roots, plus or minus 6i. So my homogeneous solution is C1 cosine 6t and C2 sine of 6t. So I look at my driving function. My driving function is 100 cosine 4t. So I'm looking at that and I'm thinking, okay, I've got a 4 here and a 6 here. So my driving function does not conflict with the homogeneous solutions. So when I do method of undetermined coefficients, I don't need any extra t's in there. All right, so this is my initial guess. I find y prime. I find y double prime, and so on. So here's y prime, here's y double prime. And so plug this into our problem. X double prime plus 36x has to equal to that. All right, so matching the double prime, the x, and the right-hand side. And so now if you match up the coefficients, I've got the cosine stuff, and the right-hand side has some cosine. So minus 16a plus 36a must be 100. And so I can solve to get that a is 5. If I look at the sine stuff, I've got a minus 16b, a 36b, but there's no sine on the right-hand side, so that's 0. And when you solve for that, you get b is 0. So my full solution looks like the following. I need to calculate x prime because I need to plug in my two initial conditions. So my initial conditions were x at 0 is 0. All right, so at 0, let's see, the sine part is already gone. I would have C1 plus 5 is 0. So C1 is minus 5. And if I plug in x prime of 0 is 0. Again, the sine parts are all missing. So I only have this one piece. And since it's 0, that says C2 is 0. And so if I plug now in what my solution looks like, it looks like a minus 5 cosine 6t plus 5 cosine of 4t. So I've got a sum of two different period cosines. If I graph this and take a look at it, the cosine of 6t has a period of 2 pi over 6 reducible to pi over 3. And the cosine of 4t has a period of pi over 2. But when you graph them as this combination, the period now is pi. Why is that? Well, if you look at the lowest common multiple of pi over 3, which is 1/3 pi, and pi over 2, which is 1/2 pi, the lowest common multiple of 1/3 and 1/2 is 1, so the lowest common multiple is pi. And that's the period for this function, which has cosine of 6t and cosine of 4t. All right, in question 2. Question 2, we have m, so we just have a mass, x double prime plus kx, k is typically our spring constant, and a driving function on the right hand side. And they're telling me that the driving functions here, omega, is going to be different from the period in here with the homogeneous solution. They're giving me an initial position, and initially it has x prime of 0 is 0. All right, so I form the homogeneous problem, get my characteristic equation. So r squared is this minus k over m, and so I get two complex roots. So at that time, we're going to let that constant be omega naught. All right, so my homogeneous answer looks like C1 cosine omega naught t and C2 sine omega naught t. So I get into the game my driving function, but remember, they don't match. The omega is different from omega naught. So my initial guess is a sum of a sine and a cosine. So I calculate x prime, x double prime, plug all this into our equation, and now it's a question of matching coefficients for undetermined coefficients. So let's see, I've got the cosine in two places and on the right hand side. So that tells me that this plus Ka must equal F0. And from the sine stuff, let's see, I've got m omega naught squared b plus kb. That must be 0. And so, looking at that, that says that b is 0. Right? And so, we plug all this now in for figuring out what a is. All right, so a was my coefficient from my guess. C1 and C2, those pieces are for the homogeneous one. And so now if you plug in at time 0, you're at x0. All right, so what happens? So at x0, all right, this part gives me a C1. Sine part is 0, and this part at 0, I just get that coefficient. And so I can solve for what C1 is. Take the large formula and find out what x prime is. Chain rule all the way across. And then you know at 0 it's supposed to be 0. Well, the good news is all the sine pieces are 0. Cosine is 1. So you get this piece must be 0. So C2 is 0. And we get our relationship that the solution is based upon the sum of two cosines of different periods, slightly different coefficients, but they are related. All right, looking here at question 3, we have a constant coefficient, second order problem on the left. We have a driving function on the right. So form the characteristic equation from the homogeneous problem. Doesn't factor, so use the quadratic formula. So as we grind through here, I see I've got a negative under a square root, so I'm going to have complex roots. So simplify that as far as we can, factoring this square root of 56 into multiple pieces. All right, so I've got, finally, my roots are minus 3 plus or minus square root of 14i. So That means, here's my homogeneous solution, and here's my driving one. There's no conflict between the driving function and the homogeneous ones. So I've got my method of undetermined coefficients guess. I find x prime, I find x double prime. Plug everything in as we've done previously, and now it's a question of matching up coefficients. So you look at all the cosine stuff, all right, cosine in a couple places, and you look at the right-hand side, and so when you do all that, you get this relationship. What about the sine stuff? Well, got some sine stuff here, sine stuff there, sine stuff there, but there's none on the right, so that's a 0. And so I get two equations and two unknowns that I can solve for a and b. And so we end up with finding b is 216 over 625. And when I find a, I've got 63 over 625. All right, so looking at that, so here's my basic solution. So I've got my coefficients of a and b in there. I've got a sine plus a cosine of 4t. All right, so since these match, I can write it as one cosine with a phase shift. And using these coefficients, I can figure out the new amplitude in the front. So how do you do that? Well, the new amplitude is the square root of the sum of the squares for each of those parts, and I got 0.36. The phase shift here is an inverse tangent of the sine part, this part here on the top, divided by the bottom. Now, both of these numbers are positive numbers, and so when I do the inverse tangent, I'm going to be in quadrant 1. And so in radians, the inverse tangent is 1.287. And so plugging all that in, I get my solution as one cosine with a phase shift. And they wanted me to compare that with 9/4 cosine of 4t. So I made some graphs of that where we can see that. All right, so when the 9/4 is here in blue, and in kind of a gold color is our solution with our phase shift, and that matches up with C. So you just got to look kind of carefully as to what matches where. And let's see, looking at question 4 here, we have a mass. It has 120 pounds, and they're giving me that its mass in this particular system of feet, pounds, and seconds is 3.75. So we don't have to do any kind of weird conversions. They're telling me the mass. And we've got a mass attached, and it stretches the spring by 4 inches with our mass. And we have a driving force that's going to act on it. And so what is the resonant frequency going to be? No dampening, so will be resonant frequency. All right, so we have this solution. So the hard part is I've got my mass, but the inches are wrong. I need feet. All right, so 4 inches converted to feet is 1/3 of a foot. And so I can figure out what is the spring constant. And so the spring constant K is 360. And so when I do that, I can find out what omega naught is just based on the spring constant and the math. If you remember in a previous problem, that was the square root of K over M. All right, so I put all that in. So omega naught is 9.79795 radians per second. And so the cycles is omega naught over 2 pi. And so about 1.56 hertz.